Hi, today I'm going to start to talk about the shear and moment diagram. Previously, we learned how to calculate the internal forces in any member. So how to calculate the uh, normal forces, how to calculate the shear forces, how to calculate the bending forces. But what we learn is that if you have a beam, we know exactly what happened in any given section. For example, let's see we have the beam as we looked previously. So if you have a beam like that that connected to the wall, and then you have a force applying on top of that, right? Uh, for example, force F, and then if we go ahead and say this, for example, ABC, so it's the A, and this end is B, and then anywhere in middle is C. If you want to know what's happening, for example, assume this is the section C, and if you want to know what's happening here, we can go ahead and cut through that section C, and then calculate the normal force for that section. But in most cases, especially when we want to design a member, we need to know what's happening throughout the beam, not in one section. We'll have to know how the normal forces change throughout the beam, how the shear forces changes throughout the beam, or how the bending moment changes throughout the beam. That's different from what we previously find the internal forces only at one section. So to know that how the internal force is changing throughout the beam, the method we are going to do is that instead of having and finding the thing in one section, we will cut through any section. So we'll go ahead and assume we cut through a section, just assume a section, it's not in any given particular location. So we cut it through, and after we cut it through, we will draw those sections most of the time. So we will and assume this cutting section here, and we don't know where it is. It's somewhere in the beam. Assume it's the point C. So we're gonna draw that. So we have the A, C, and then we have the CB. When it comes to these kinds, so it is a and the C and the CB. And for these cases, when we draw the internal forces, we'll go ahead and say the internal forces, we have the normal forces, we have the shear forces, and then we have the bending moment at that particular position. And we don't know that position, where is that position. And also we have the those what we say the uh, support for the point A. So we have the AX, we have the AY, and we have M at A. So we have the support and we have the internal forces. In this case, the distance we are going to consider is that we will say that the distance from here to the section, exactly from the start to the section, we will consider it as a x. And in most cases, so we are not going to be worried about this CB section. We only worry about this part. And then we start to write the equation for equation equilibrium for this section. So we write the sigma f x is 0, and then we write the sigma f y is 0, and then we write the sigma m, mostly about the section, but it can be written about any point. But we write the sigma m is 0, and then eventually these three gives us the set of equations, gives us n as a function of x. Also, it gives us v as a function of x, and it also gives us m as a function of x. So by doing that, we will have n, v, and m as a function of x, and then we can draw them as a function of x going from here, for example, from a to b. It can be anywhere from a to b, and then when we're changing x from a to b, then we will find and we can draw this equation, and then we can see how the internal forces change within that beam. Now it's a question that when we want to deal that where we're actually going to put that section, and there are some couple of rules that we need to know about that. So here I'm drawing another beam, and I will explain how we are going to just uh, cut through a beam if we need it. So assume I have a beam like that. There's a and then we have external forces. So we have part of that, we have distributed load, and then we have a single load F1, and then we have another load F2 here, and then the reaction of the support. Assume we have the, and this is the point, assume say AY AX, assume it's a DY, and the points we have, assume this is the point A at the start. At the end of that distributed load is going to be B, and then we have C underneath of that single load. Then we have D here for this support, and then we have E toward the very end. So where we are going to put where we are going to have the section, that's the point, is that anytime we have the distributed load, we need to have a section in the distributed load. Also, between any two sets of load, we need to have a section. So here we have a distributed load goes from A to B, so we need to have one section from A to B. And then there's a between two sets of load, basically whenever there is a change in load. So we have in distributed load finish here, and then there's another load here. So from B to C, because there's a change between these two sets, we need to have another section. Then between these sets and these sets, so between F1 and dy, because there are two sets here, we need to have another section. And then between dy and F also we have to have another section. So between every two sets of force, single force, we need to have a section. Also, if we have a distributed load, we need to have one section in that distributed load as well. So I'm going to start that to the very first section is that if I go ahead and it says that I will need to have one section here, and I will name it section 1. So for that section 1, if I want to write that in the section 1, what I have is that again it says the X is start to go from the beginning to that section. So if I want to write that, so I will say that X start from, so X is going to be between A and B. And for that section that I have X between A and B, I can go ahead and write that, draw that section and put the force on that. So if I draw the section, I can go ahead and say this is the section I have. So it's between A and B. So we have the A, and we have the, for that section we have AX, we have AY, and then we have the distributed load on top of that. But the distributed load is going to, we have part of that distributed load. We are not going to have the whole distributed load because we cut through that distributed load. And then we have those internal forces here. So we have the N, and we have V, and we have M. Now that we have this, we can go ahead and write the three equilibrium equation for that. So mm, for this case, for example, if I go ahead, we first remember whenever we are cutting through the section, we have the distribution load. Don't touch the distributed load until you cut it through the section, and then replace it with the force. And also this distance is going to be x. So x is always a start from to the very left of the beam we have. X is going to be a start always from A and to the section. So that's going to be the x for our section. And for this section, if I go ahead and start to write the first, I need to replace this force with uh, um, let's say the resultant force. If I go ahead and replace it with the resultant force here, so this is going to be the resultant force. So that resultant force, that's the resultant force here, and the magnitude of that resultant force is whatever we have for that resultant force will represent here. So the intensity of the force, and assume the intensity of that force, for example, is um, I'm not going to put a number, but for anything is for the intensity of that force, you can put it there. So that's the resultant force, we can put it there. And this distance here, this is going to be right at the center, so this distance here is going to be just x divided by 2. The same also on the other side. So if I go ahead and write the sigma fx equals 0, so I can go ahead and say that I will write a sigma fx is 0 for this section, and then I can write a sigma fy is 0 for this section, and I can write sigma m is there. So if I, for example, let me write this. If sigma fx is 0, I would say that, for example, it will give me some equation for the end, and then I can go ahead and write the sigma fy is 0, and then I can write the sigma m is 0 for that section. And these three equations is going to give me three equations for which are going to be based on the x value, the x value I have here. Now that I have this section, after I write and give that section, I will go to the next section. So let me well, so if I want to go to the next section, so the next section would be, if I go to the from the I will down with this distributed load. The next one is between the distributed load and the next one. So between these two sets of force, that's where we're gonna have. So again, if we have a distributed load, we need to have section between that distributed load on. So we need to have a section between every two sets of load we have. So it's gonna be section 2. It's gonna be section 2. So we have the section 2, and that section 2 is gonna be between if I put it there, the section 2 is gonna be between the section is gonna be between B and C. So the X is gonna be between B and C. Still X start, the origin of X start here, but X we go from here to here, from B to C. This is where we're gonna look at that. So if I draw that, the free body diagram, that is what I'm gonna have. So so I have the X, again I have the AX, have the AY, and then I have those the same N, V, and M. Also here N should be in the other direction. I made a mistake here. So the N should be this way. Same here, so n is that way. So we have nvm. We have the force on top of that, so we have the um, force on the distributed force, and this time we have the whole distributed force, so it's not the part of that, so we have the whole thing. And so this is the point A, it's the point A, here is the point B, and between B and C is somewhere that we cut through, and that's where we called it X. And again, X start from the beginning and go to the section, and that's where we are going to write again the sigma of X, sigma of Y, sigma M equals 0, and find these internal forces for that section. Then we will need to go ahead to the next section. So again, we have that. Then again, after that, for the next section, anytime force change between any two sets of forces, this is what we are going to have. So it's the same thing we are going to have for section when we are between C and D. So when X is between C and D, so X is between C and D. Again, the origin of X is A, but this time, so X, the 0 is here, but this time we'll look at that X change from C to D, whatever is that magnitude. And we cut the section somewhere in there, so we cut the section somewhere here, and call it the section 3. And then we will go ahead, I will go ahead and draw that section as well. So if I go ahead, I have A, B, C, and then I have the section. So again, I have the external forces at A, so I have the AX, AY, I have the distributed load, the total distributed load here. And also remember, eventually we are going to replace it with the resultant value for that force. And then I have the at F1 FC, I have the F1 here, and so this is the point A, this is the point B, this is the point C, and between C and D we cut it through, and we have the N, and we have the V, and then we have the M. This is how we're gonna have, and again the X would be a start from here and it goes all the way to the cross section, so that's the X. But this time we are interested for the X start from the C and end at the D, and we again write this equilibrium equation and we will find that. And the last section we need to have, the last section would be we have to cross it again between D and E, between these two sets, because again we have two sets of force, so that's the section 4. And the very same thing, we cut it at the section 4, and again we draw the free body diagram for the X going between D and E. So X start at D and end at E, and we draw the free body diagram and then find the internal forces. Each of these sections we draw, it will give us the same. So I will also put it up here. So for the very last section, if I put it up here, so we'll see that for the section again X between D and E. If I draw that, we will have again we put all the external forces on that, so we have the AX, AY, and we have the also the dy is here, and then we have the external forces, the distributed load, have the whole distributed load, and then we have the F1, uh, have the F1 here, and then we have the internal forces N, V, and M. And we will go ahead and do the calculation again. The X is going to be point A here, this is point B here, this is point C, and this is point D, and we are somewhere between D and E. And again, the X is start from the origin always and goes all the way to the section. So that's the same. I will write that. So by doing that, for each section we'll write the section, we will write the equilibrium equation, and by doing that we get the N, V, and M as a function of X for each section, and then we just need to draw those sections, draw the equation for those sections, and then we have the diagram of the normal force, the shear force, and the bending moment throughout the beam. Okay, now let's look at an example. Assume we have a beam that's going from A to B, and then we want to find the we want to draw the shear and moment diagram from A to B. See how the shear diagram and the moment change through this beam. So the very first thing we need to do is we need to find the reaction at point A and B. So I will draw the free body diagram here. So if I draw the free body diagram here, and we have the AY, AX, and we have B, and then we have the 20 Newton here apply here, and then for we have the distributed load, which I'm gonna replace it with a single resultant force. So if I go ahead and replace that with single resultant force, and it's gonna be the area underneath of that distributed load, which is the 10 times 3. So it's the 10 times 3, which is 30, and the distance from here to is the half of this, because it's going to be at the centroid of this rectangle. It's going to be right in the middle, and it's going to be half of this, so it's going to be 1.5 meter. So it's a distance, and now we can write the equation of equilibrium. So I will write it here. So if I write the sigma fx is 0, the very first thing is sigma fx is 0 will gives us that ax is going to be 0. So there are no horizontal forces. And then if I write the sigma m about point A is 0, and assuming the counterclockwise is positive, so we calculate the moment about point A. So ax and ay doesn't have any moment about point A because both of them pass through that point. And then we have the forces that they have is that resultant force here, this 20 Newton, and the By. So these are the three forces that they have the effect on that. So if I write that, if I go ahead and write the sigma Fy is 0, it's basically for the very first one, and this one is going to be 30, the force is 30, and the distance between force, the normal distance between force and A is 1.5, and respect to the point A is going to rotate it like that, so it's going to be clockwise, so it's going to be negative, so it's going to be a negative sign here. And then for 20 we have the 20, and the normal distance between 20 and A is 4, so it's from here to here is 4. And again, respect to point A is going to rotate it like that, so it's going to be is going to be clockwise, is going to be negative as well. And the by, the normal distance for the by with A is 5. And the by is about point A is going to rotate it, the beam like that, so it's going to be clockwise, counterclockwise, so it's going to be positive. And it is 0, and if we do the calculation, the by would comes out as 25 Newton. And then if I go ahead and I write the sigma, if y is 0, uh, in that case what we have is ay plus by minus 30 minus 20 is 0, and we know the by is 25, so therefore if we go ahead, we will get the ay is also 20, it's also 25 Newton. So these are the forces we have, and I'm gonna just put them on the beam itself, so can clean that. So if I go ahead and say, so the ay, this is the 25 Newton, and we have the by equal again with 25 Newton. So these are what we are gonna have for our let's say reaction of the support, or support reaction. Now that we have the reaction of support, we have to go ahead and cut through our beam to find the shear and the moment throughout the beam. Remember, anytime we have a distributed forces, we have to have one section through the distributed force. So that's one thing that we have to do. The other thing that we have, anytime we have two sets of force, between two sets of force, we should have the section. So we need to have one section in this distributed load, and then between these two sets we need to have one section, and between these two sets also we need to have one section. So we need to have in total 3 sections for our calculation. So to start doing that, I'm gonna okay, so we'll start first with that section that we have the distributed load. So if I go ahead and to that, for in that case the x is between 0 and 3. So if I have the x, if I say that x between 0 and 3, in that case, well, for that case I can go ahead and say, so if the x is between 0 and 3, I can draw my beam. So in somewhere, let's have it. So we have part of that distributed load, we don't have the whole distributed load. So it's going to be the distributed load, and then we have 25 Newton here, and then we have these internal forces. So we have the N, we have the V, and we have the M. That's all we have. So I'm going to just replace this distributed load with the resultant one. So it's going to be right in the middle of that, and the magnitude of that is going to be so let me show, and that's the distance. So it goes from here to here, so that's the x. In that case, the magnitude of that is going to be let's see, the area underneath of that distributed load, which is going to be, the magnitude is 10 times x, so it's going to be 10x is going to be the magnitude of that, and the distance of that force up to here is x over 2. So that's what we have. And in that case, if I go ahead and start to write the equilibrium equation. So if I write here the sigma fx is 0, it gives me that the n is 0. And then if I write the sigma fy is 0, it will gives me the, if I can write it, so I have the 25 Newton upward, and then I have the 10x downward, and then I have the v downward as 0. So these are the forces I have. There's no other forces there. So therefore the v would become at 25 minus 10x. And then if I write the sigma m about the section, and if I let me show the section 1 is going to be anywhere there. So it's under section 1. So anywhere there. So if we write the moment about the section is 0. If I write it, so n and v doesn't have any moment about that section, and the forces that have section is that 10x, is that 25, and the m. So in that case, if I write it here, I'm gonna have a start with 25, so it's gonna be 25, and the distance between 25 and the section is x over 2, and then and it's also rotated clockwise, so it's going to be negative. Then I have this 10x, so it's going to 10x, and its distance is, the normal distance has is also x over 2. The distance from here to here is x over 2. And it's about 0.8. If I look at it at 0.8, about 0.8 is going to rotate it counterclockwise, so it's going to be positive. And then we have the m itself, which is rotated counterclockwise, equal to 0. And if we write that equation, it's going to give us m equal to negative 5x squared plus 25x. So if you look at here, we have the v as a function, so we have the v as a function of x, and we have the m as a function of x here. So we can, in that section, then we need to go to the next section and start to do the same thing for the next section again. Go ahead and then look at the next section. We have to that. So between, that was the first section. If you have distributed load, we need to have one section in that distributed load. Then between every two sets of load, so there's one set and there's another set. So we have our second section is going to be here. So it's going to be our section 2. That's the second section. So the x for that section is a start right here at 3 and end right here at 4. So x is going to be between 3 and 4. So for the first one is start 0 to 3, and for the second one 3 to 4. And if I draw the free body diagram of that, this is what we have. So we have the 25 Newton at A, and then we have this time we have the entire distributed load, and that's all we have for the external forces. And then we have the internal forces also. That's going to be N, it's going to be V, it's going to be M. So we have these three, and then we can go ahead and replace this distributed load with the resultant force. and its magnitude is going to be, this time we have the entire distributed load, so it's going to be 10 times 3, is 10 times 3, so it's equal to 30. So that's the whole, and the distance also is going to be, this distance is so 1.5, and then that's the x, which is going to be always from the here to the section. So that's going to be the x that we need. Then it comes to the if you want to know that distance here, there's that's the part, the distance on the other side of that. So it's going to be x minus 1.5. So there's the whole thing is x, and it's what here. So again, if I go ahead and write the sigma fx is 0, just tell me n is 0. And then if I go ahead and write the sigma fy is 0, what I have again here, I have the 25 here, and then I have the 30, negative 30, and then I have the negative v. So all the forces I have, therefore the v would comes out at this time we will have the negative 5, and you'll see this time is going to be constant. And then if I write the sigma m about the section, but this time about this section here, equal to 0, what I'm going to have, so v and n doesn't have any moment about that section, because both of them pass through that section. So we don't need to be worried about that. So we have to go here and look at this force and this force. These two have the moment and the bending moment itself. So again, if I look at that, the 25 is going to be negative 25. So it's similar to previous one. So it's going to be 25 times 20 times x. So this is the moment for that, and it's going to rotate it clockwise, so it's going to be negative. And then we have this 31, so it's going to be 30, and the distance is x minus 1.5. That's the distance between force and there. And it's going to rotate it counterclockwise about the section, so it's going to be positive. And then we have the m itself, which is rotate counterclockwise, so it's going to be positive m 0. And then if we do the calculation, it's going to give us m is negative 5 x plus 45 Newton meter. So then it's going to be ahead. This is going to be our equation for the m when we go between for that section, and this is the v. It's going to be constant in that section. Now that we have for these two sections, the last one we need is again another set of sections. If I go ahead, the last one is going to be here, so we will need to have one section here, so it's going to be section 3 between two sets of force. There are another two sets of force, so we need to have another sets of equation for that section. So I will going to clean this area and then write it there. So for that section, what we have is, if I go ahead and say we have now this time the x is uh, between 4 and 5, so we start from 4 and 5, so x is going to be between 4 and 5. And if I draw that section of the beam between 4 and 5 and put all the external forces we have on that. So we have the 25 Newton here, and then we have the distributed load. Also we have the entire distributed load. And then we have these 20 Newton here. And then that's the end of that section. And if I go ahead and replace that distributed load with the resultant force, again it's going to be the entire force is there, so it's going to be 10 times 3, so it's going to be 30. And the distances we have, again the x is going to be from all the way from here to here, so that's the x. That's what we have for the x, and that is the other we know, and also the internal forces themselves. And if I go ahead and write again the sigma fx is 0, it gives me the n is 0. And then if I write the sigma fy is 0, what I'm gonna get, again I have the 25 is positive, I have 30 negative, I have 20 here negative, and I have v also negative is 0. Therefore v would comes out as negative 25 Newton. And then if I write the sigma m about the section is 0, again about that section is 0, so I have that 25 times x again, so there's 25x, and it rotates about 0.8, is going to rotate counterclockwise, so as always we consider this as positive, so it's going to be clockwise, so it's going to be negative because it rotates like that. And then we have that 30, and the distance for that 30, if I want to show that distance, we know that the distance from that 30 to this side is up to here is 1.5, and therefore this distance is x minus 1.5. So that's the same thing that we have the x minus 1.5, the distance, and also it rotates counterclockwise, so it's going to be positive. And then we have these 20 here, and for the 20 it's going to be the same thing for it's a similar thing for the distances. If I want to show that, for example, if I go ahead and here this distance up to here is the 3 and 4, and this distance is going to be x minus 4. So it's a 20, so we have this 20 Newton here, and the distance, the normal distance is 20, and the section is x minus 4. And it rotates counterclockwise, so it's going to be positive about the section is going to be counterclockwise. And then we have the m, which is rotate counterclockwise, so it's going to be positive and 0. And then if you do the calculation, m would becomes out negative 25x plus 125 Newton meter. So this is going to be the v between the 4 and 5, and this is going to be the m between 4 and 5. So now we have the equation, we have all the equation between them, between all the section. We can go ahead and you know, draw those equations, and by drawing those equations, what we get is the shear diagram and the moment diagram. Okay, I redraw that beam, and these are the equation we have for every section, and then I'm gonna to draw the shear and moment diagram. So first I will start with the here's the shear diagram. If I go ahead and get, so that's the X, that's gonna be our shear diagram, and we are going to, so we'll look at the, let me bring down here, so we'll also bring down these lines. So at the beginning, if I put for the shear, I start between 0, I will draw that one between 0 and 3. So for x is 0, the shear is going to be 25. So I know that it's start from 25, assume this is a 25. So I start at 25. And then if I put it, I use that word, put the 3 here. So I'm going to be the 25 minus 30, so it's going to be negative 5. So I'm assuming this is negative 5, and then it's a linear one, so it goes from 25 negative 5 linearly. And then when it gets to that between 3 and 4, we know that the v is constant. It's going to negative 5. So between 3 and 4 is constant, doesn't change. And then between 4 and 5 is also constant, it's negative 25. So it goes down there. It is a 25 here, assume it's 25, so it's also constant. It comes here and then eventually comes back to 0. So this is our shear diagram. Says, and it's this part is also negative 25. So it starts from 25, so this part is 5, and then negative 25 and back up there. So this is how we get our shear diagram. The next one is we'll draw similar to that. We'll draw the moment diagram. So it's going to be our moment diagram. So this is the X, and this is the M, and then go ahead and bring down these lines. So for the shear the moment diagram, they were the same. So here we have the M and negative. For this one, we will put 0. If we put 0, it's gonna be 0 here. You start from the 0, and then eventually, if we draw that, and if we put 3, is we would come at 30, and this is something that we will have something like that here. Let me see that. So if we draw that, you can go ahead and draw that. That's what we will get, something like that we will get. And then from here it's going to be at this point it's going to be 30. So we'll write that. So it's going to be 30 here, and then from here between 3 and 4 is going to be linearly going down. So if I put the 3 there, um, uh, uh, it's going to be negative 15 and 45, so it's 30, so it's exactly the same location at that the other one end. And if I put 4 there, it's going to be negative 20 and 45, so it's end up being 20, 25. So it goes from here to 25 linearly. So it goes to 25, and then from here, if I put 4 here in that, this is going to be negative 100, and it's going to be 125, so it's going to 25. And if I put 5, this is going to be 0, so it goes from there to 0. So that's what we'll see. That's going to be our shear diagram. The so there's a moment diagram. Now there are a couple of points that I want to mention here about uh, what we have here, and these points generally can be used as a guide, sometimes to check what we have done and what we get. The very one of the very first thing you probably need to look at that is that look at the very beginning and the end of the beam we have. If you look at the very start and end of the beam here and here, what we see that is both of them goes to 0. So it's 0 here, and it's also 0 here. The whole point is that if we have the let's say pin or roller that they are not going to withstand the moment, and they are at the end of the beam. That's the important point. They should be at the end of it. So if you have the roller or pin at the end of the pin, always moment at that support is going to be 0. If this one, for example, this point B, instead of being at the end of the beam, it was somewhere in the middle of the beam. For example, if it was here, assume this one was here. Then in that case, the moment was not 0 because it's not at the end of the beam. Only if it is at the end of the beam, the moment at those end of the beam is going to be 0. If we have the roller like that, or we have the pin support, roller support or pin support at the end of the beam, those locations, the moment is going to be 0. So that's one point that you always, if you see that, for example, if you calculate anything but 0 at these points, then we would say that we would know that something is not right. The other point is that we will have the let's say dv over dx is equal to w, and if you say that this one is the slope of this one is the slope of shear, and this one is just distributed load. So basically the slope of the shear is equal to the distributed load, and remember why it means that we have to consider the direction of the load as well. So for example, here the load look downward, so it's going to be negative because the load is downward, and if the load is upward, it's positive. So look at here, we have there's a distributed load we have here, and it is 10 and it's downward. So the distributed load is 10 and it's downward. And look at here what we have, and what we have here, if you look at the slope of that line, it's the slope of the line here. So you see it's negative 10. So the slope of that and the slope of shear are the same. So it's what's it here in between this area, there's no distributed load. There's no distributed load from here to here, so the distributed load is 0. So as you can see, it's constant. It doesn't have any slope. And also the same here, from here to here, there's no distributed load. So there's no slope. It's going to be a stay constant. So that's one thing that we can always use to check our calculation to make sure that what we are doing is right. Similar to that, another point that we have is like that, so we can write the dm over dx is equal to v, and so this part is the slope of bending moment, and this is the shear. So again, the slope of the moment diagram is equal to shear. So any time that we have the slope of that, we will see that, for example, here, if you look at here, this is the shear and this is the slope. So we can see that here, the slope of that line here is equal to the shear. The same here. So this is the slope and this is the shear. So they are the same. And the same down here. So this is the slope and this is the shear. You can see both of them are the same. You can see it more easily in the linear one. The same is here. Also, you would see that fact also as well there. So the slope, you will see the slope keep decreasing, and the slope of the moment decreasing, and then the slope becomes 0. So it reached to the slope here also 0, and then the slope is negative, and so the slope of that moment become negative here as well. The other point, and this one is also related to that point, is that another one is sort of, anytime that we have the shear, anytime that shear is 0, the slope is going to be in its extremum value. So look at here. So basically this is here, it is 0, and here is going to be max, because when the shear is 0, the slope, when the shear is 0, it means the slope of the moment is 0, so it's going to be max, or it might be on the other side. So magnitudely is going to be maximum, or it's going to be on the other side. As a magnitude x still, so minimum can be the minimum, but down here, so its slope is 0. So you can look at that anytime that you have the shear becomes 0, you have to go ahead and look for the 0 slope on the moment diagram, but basically it's going to be maximum there. If it's positive, it's going to be max there. And another one to mention, to remember. Also, the other points, that anytime that we have the force, the single force, so anytime that we have the single force cause to have jump in shear. So if you look at here, this force, basically we have a 25, so it jumps up here, so it goes to 25, and then this distributed load pushing is downward, so it goes up, goes down up to here, and then there's no force, so it will stay constant because there's no force. And then we have 20, so it's going to be jump 20 down there because it's going down, goes down to 25, and then there is no force, so it's going to stay constant. And then we have 25 upward, so it's going to jump 25 up. So basically anytime that you have the single force like that, you will see that you have a jump. So you have a 25, so it jump to 25, then here you have 20 down, so it's going to jump down 25, and then here you have 25 up, so it's going to jump up 25. If you had the moment, the single moment anywhere on the set, so you would see the jump on the moment diagram as well. These are some of the points that we can use when we are drawing. So it helps us to make sure, at least sometimes when we get more comfortable, we can use it to draw, and also it helps us to double check and make sure that what we draw was right, or we make sure that we haven't done any mistake in our drawing.